There was no silence before the universe began, because silence requires time in which to stretch, and time itself had not yet learned how to exist. There was no darkness, because darkness implies the absence of light within a space, and space had not yet unfolded its dimensions. What we call the beginning is not an event placed neatly on a timeline, but rather the violent and paradoxical birth of the timeline itself, a moment when physics, language, and intuition all begin to fail in equal measure. Modern cosmology, grounded in Einstein's general relativity, once described this beginning as a singularity, a point of infinite density and zero volume where the known laws of physics collapse into mathematical ruin. Yet even this picture, long taught with confidence, is now under scrutiny. Recent theoretical work suggests the universe may not have emerged from an actual singularity at all, but from a finite, highly energetic state governed by quantum gravitational laws that tame the infinities once thought unavoidable. To understand why this matters, one must first accept a difficult truth. The universe is not obligated to be intuitive. The mathematics that describes its birth is precise, predictive, and experimentally grounded, yet utterly alien to the human imagination. We are creatures evolved to throw stones and judge distances, not to comprehend a cosmos that expands faster than light can traverse it, or a beginning that is not located in space, but is instead the origin of space itself. The prevailing framework, the lambda cold dark matter model, still describes the large-scale evolution of the cosmos with remarkable success. It explains how matter clumped, how galaxies formed, and how the universe continues to expand. Yet, even this model shows fractures under the weight of new data. The so-called Hubble tension, a persistent disagreement in measurements of the universe's expansion rate, hints that something subtle but fundamental may be missing from our understanding. And then there is the telescope that has, more than any instrument before it, begun to peel back the first chapters of cosmic history, the James Webb Space Telescope. Its observations have pushed our vision to within a few 100 million years of the beginning, revealing galaxies that should not exist so early. Massive, luminous structures that appear to have formed far more quickly than our models predict. These discoveries do not overturn the story of the universe's birth, but they complicate it, enrich it, and perhaps most importantly, remind us that we are still at the edge of understanding. The beginning of the universe is not a solved problem. It is an active frontier where observation and theory collide, and where each new discovery forces us to reconsider what it means to say that something has a beginning at all. If we insist on telling the story chronologically, and physics, for all its abstractions, still allows us to do so, then the earliest meaningful chapter begins not at time zero, but at a fleeting instant after. The Planck time, roughly 10 to the power of minus 43 seconds after the beginning. Before this threshold, our equations dissolve into uncertainty. Beyond it, the universe becomes, in principle, describable. In that first fraction of a second, the universe was not made of atoms, nor even of protons or neutrons, but of a seething, incomprehensibly hot plasma of fundamental particles. Temperatures exceeded anything that would ever exist again, so extreme that the familiar forces of nature had not yet separated into their distinct identities. Gravity, electromagnetism, and the nuclear forces may have been unified in ways we are only beginning to mathematically reconstruct. Then came inflation, a theory both elegant and unsettling. It proposes that the universe underwent an exponential expansion, doubling in size again and again in a tiny fraction of a second, stretching quantum fluctuations to cosmic scales. These fluctuations would later become galaxies, clusters, and the vast cosmic web itself. Inflation explains why the universe appears so uniform on large scales and yet contains the seeds of structure on smaller ones. Yet inflation too is under quiet revision. Some modern theories suggest that inflation-like behavior could emerge naturally from quantum gravity itself, without the need for hypothetical fields added by hand. These approaches aim to unify the beginning of the universe with the laws that govern it today, removing the need for special initial conditions. As the universe expanded, it cooled. Within microseconds, quarks combined to form protons and neutrons. Within minutes, the first atomic nuclei formed in a process known as Big Bang nucleosynthesis. Hydrogen and helium, simple, primordial, became the raw material for everything that would follow. Stars, galaxies, planets, and eventually, the chemistry of life. For hundreds of thousands of years, the universe remained opaque, a dense fog of charged particles scattering light in every direction. Photons could not travel freely. They were trapped in an endless dance of interaction. But as the cosmos expanded and cooled further, a transition occurred. Electrons combined with nuclei to form neutral atoms, and light was finally released to travel unimpeded. This ancient light still exists today as the cosmic microwave background, a faint afterglow permeating all of space. It is not merely radiation, it is a fossil, a snapshot of the universe when it was just 380,000 years old. Tiny fluctuations in its temperature encode the initial conditions from which all cosmic structure grew. And yet, even here, new observations continue to refine the story. Precision measurements of the cosmic background, combined with large-scale surveys of galaxies, are revealing subtle discrepancies that may point toward new physics, perhaps in the nature of dark matter or in the behavior of dark energy itself. For decades, cosmologists believed they had a reasonably complete timeline, a hot Big Bang, a period of inflation, a gradual formation of structure. But the universe, it seems, is under no obligation to conform to our expectations. The latest observations from the James Webb Space Telescope have revealed an early cosmos that is far more active, more chaotic, and more productive than predicted. Galaxies appear earlier than expected, some already massive and mature within a few 100 million years. Dust, once thought to require generations of stars to produce, is present in surprising abundance, suggesting alternative pathways for its formation. Even more striking is the rapid emergence of black holes. Supermassive black holes, millions or billions of times the mass of the Sun, are found at epochs when the universe was still in its infancy. Their existence challenges traditional growth models and suggests that either black holes formed from unusually massive seeds or that they grew at rates far exceeding previous limits. Underlying all of this is the invisible scaffolding of dark matter, whose gravitational influence shaped the earliest structures. Recent mapping efforts have begun to reveal this hidden framework in unprecedented detail, showing how it guided ordinary matter into the filaments and clusters that define the large-scale universe. To understand the beginning of the universe in its fullest sense, one must descend beneath particles, beneath fields, beneath even the familiar scaffolding of space-time, into a domain where reality itself becomes granular, uncertain, and profoundly strange. Here, in the realm of quantum gravity, the universe is no longer a smooth continuum, but something more akin to a fluctuating tapestry, threads of existence weaving in and out of definable being. Einstein's general relativity describes gravity as the curvature of space-time, a geometric elegance that has passed every experimental test on macroscopic scales. Quantum mechanics, by contrast, governs the microscopic world with probabilistic laws that resist deterministic interpretation. For over a century, physicists have sought to reconcile these two frameworks, because at the beginning of the universe, both must operate simultaneously. And yet, in their current forms, they cannot. Several competing approaches attempt to bridge this divide. Loop quantum gravity proposes that spacetime itself is quantized, composed of discrete units woven into a network of finite loops. In this picture, the Big Bang is not a singularity, but a transition, a bounce from a prior contracting universe, where density reaches a maximum but never becomes infinite. String theory offers a different vision, that the fundamental constituents of reality are not point-like particles, but vibrating strings existing in higher dimensional space. In some formulations, our universe may be a three-dimensional brain embedded within a larger multi-dimensional structure. Collisions between such brains could, in principle, trigger events that resemble what we perceive as the Big Bang. More recent theoretical work, emerging in the mid-2020s, suggests that space-time itself may be an emergent phenomenon, arising from deeper quantum informational structures. In these models, geometry is not fundamental, but constructed from entanglement relationships between underlying quantum states. The beginning of the universe, then, is not the creation of space and time, but the reorganization of information into a form that gives rise to them. Inflation remains one of the most powerful ideas in cosmology, yet also one of the most enigmatic. It proposes that the early universe expanded at an exponential rate, driven by a field whose energy density remained nearly constant for a brief but crucial interval. This rapid expansion smoothed out irregularities and stretched quantum fluctuations into the seeds of cosmic structure. The evidence for inflation is indirect but compelling. The large-scale uniformity of the universe, the near flatness of its geometry, and the specific statistical pattern of fluctuations in the cosmic microwave background all align with inflationary predictions. Yet the identity of the inflationary field, the mechanism that powered this expansion, remains unknown. Some modern refinements suggest that inflation may not have been a single isolated event, but part of a broader landscape of possibilities. In certain models, inflation occurs eternally, giving rise to a multiverse in which different regions of space experience different physical laws. Our observable universe would then be just one bubble among many, its properties shaped by chance as much as necessity. Other approaches challenge inflation altogether, proposing alternative mechanisms to explain the observed structure of the universe. These include bouncing cosmologies, where a prior contraction phase imprints the necessary conditions, and emergent universe models, in which the cosmos exists in a quasi-stable state before transitioning into expansion. After the universe became transparent, it entered a period often called the Cosmic Dark Ages, a time before stars, before galaxies, when matter drifted under the quiet influence of gravity. Over tens of millions of years, tiny density fluctuations grew, pulling gas into increasingly dense regions until at last the first stars ignited. These primordial stars, known as population 3 stars, were unlike anything that exists today. Formed from pristine hydrogen and helium, they were likely massive, luminous, and short-lived. Their nuclear furnaces forged the first heavy elements, carbon, oxygen, iron, seeding the cosmos with the ingredients necessary for planets and life. The death of these stars was equally transformative. Exploding as supernovae, they enriched their surroundings and triggered further waves of star formation. In their cores, or in the remnants they left behind, the first black holes may have formed, seeds that would eventually grow into the supermassive giants observed today. Recent observations have begun to probe this era more directly. By detecting the faint light of early galaxies and analyzing their chemical composition, astronomers are piecing together the timeline of stellar birth and evolution. Yet many questions remain. How massive were the first stars? How quickly did they form? And how did their influence shape the structure of the young universe? On the largest scales, the universe resembles a vast, intricate web. Galaxies are not distributed randomly, but arranged along filaments of matter stretching across hundreds of millions of light years, intersecting at dense clusters and separated by enormous voids. This structure is the direct consequence of gravity acting on the initial fluctuations imprinted in the earliest moments. Dark matter plays a central role in this architecture. Though invisible, it outweighs ordinary matter by a factor of roughly 5 to 1, providing the gravitational backbone upon which galaxies form. Without it, the universe as we know it, rich with structure and complexity, would not exist. Simulations of cosmic evolution running on the most powerful supercomputers have recreated this web with remarkable fidelity. By starting from initial conditions derived from the cosmic microwave background, these models produce structures strikingly similar to those observed, and yet subtle discrepancies persist, hinting that our understanding of dark matter may still be incomplete. Some theories propose that dark matter is composed of new particles yet to be detected. Others suggest modifications to gravity itself. The resolution of this mystery will not only illuminate the nature of the cosmos today, but also refine our understanding of its earliest moments. One of the most profound questions about the beginning of the universe is not simply why it exists, but why time flows in a particular direction. The laws of physics, at their most fundamental level, are largely time-symmetric. They do not distinguish between past and future. And yet, our experience of reality is defined by an arrow of time that moves inexorably forward. This asymmetry is deeply connected to entropy, a measure of disorder. The early universe appears to have been in a state of extraordinarily low entropy, despite its high temperature and density. As the universe expands, entropy increases, giving rise to the thermodynamic arrow of time. But why was the early universe so ordered? This question remains one of the great unsolved problems in cosmology. Some theories suggest that inflation naturally produces low entropy conditions. Others propose that our universe is one of many, and that we observe it in this state because such conditions are necessary for observers to exist. In this sense, the beginning of the universe is not merely a physical event, but a boundary condition for the emergence of complexity, structure, and ultimately consciousness itself. The arrow of time is the narrative thread that allows the cosmos to evolve from simplicity to richness, from a nearly uniform plasma to a universe capable of contemplating its own origins. We stand, even now, at the threshold of comprehension. The beginning of the universe is not a fixed story etched into the fabric of knowledge, but a living question, one that evolves with every observation, every equation, every insight wrested from the interplay of theory and experiment. New observatories, both on Earth and in space, are poised to push our vision even further back in time. Gravitational wave detectors may one day capture signals from the earliest instants, offering a direct probe of inflation or its alternatives. Particle accelerators continue to search for hints of the fundamental laws that govern the universe at its birth. And perhaps most intriguingly, entirely new frameworks of thought are emerging, approaches that treat information rather than matter or energy as the most fundamental constituent of reality. In such views, the universe is not merely a physical system, but a computational or relational structure, evolving according to principles we are only beginning to articulate. The story of the universe's beginning is, in the end, a story about limits, the limits of knowledge, of language, of imagination. And yet, it is also a story about transcendence, about the ability of the human mind to reach beyond its origins and grasp, however imperfectly, the vastness from which it arose. To ask what came before the beginning is to trespass into a region where language becomes treacherous. The phrase itself, "before the Big Bang," assumes that time extends beyond the boundary at which it was, by all current understanding, born. And yet, physics has never been content with boundaries. It presses against them, tests their limits, and, when necessary, redefines them entirely. One class of theories proposes that the universe did not begin in a singular act of creation, but emerged from a prior phase of contraction. In these bounce models, the cosmos cycles through periods of expansion and collapse, each transition governed by quantum gravitational effects that prevent the formation of true singularities. The Big Bang, in this view, is not the beginning of everything, but the end of something else. Evidence for such models remains indirect, but researchers have begun searching for subtle imprints, patterns in the cosmic microwave background, or in the distribution of galaxies that might distinguish a bouncing universe from an inflationary one. So far, the data neither confirms nor rules out these possibilities, leaving them suspended in a state of tantalizing uncertainty. Another possibility is more radical still, that time itself emerges from a deeper, timeless reality. In certain quantum cosmological frameworks, the universe is described by equations that do not include time as a fundamental variable. Instead, time arises as an emergent property, a way of ordering correlations between quantum states. The beginning of the universe, then, is not a moment in time, but the point at which time becomes meaningful. There exists a hypothesis, both elegant and unsettling, that our universe may be the interior of a black hole formed in another, larger cosmos. In this picture, the gravitational collapse of matter in a parent universe gives rise to a new region of space-time, our own, hidden behind an event horizon and forever inaccessible to its progenitor. This idea, sometimes called black hole cosmology, offers intriguing solutions to long-standing problems. It naturally explains why the universe began in a state of high density, and it may even account for certain features of its large-scale structure. Some formulations suggest that each black hole could spawn a new universe, leading to a kind of cosmic evolution where universes that produce more black holes become more common. While deeply speculative, this framework has gained renewed attention in recent years, particularly as observations have revealed the ubiquity and rapid growth of black holes in the early universe. Whether these objects are merely inhabitants of our cosmos or gateways to others remains an open question, but one that sits at the edge of both physics and philosophy. If true, such a model would transform our understanding of beginnings entirely. The birth of a universe would no longer be a unique, singular event, but part of an ongoing, generative process, a cosmic lineage extending beyond any single horizon of observation. Inflation, when extended to its logical extreme, gives rise to a profound and controversial possibility that our universe is not alone. In many models, inflation does not end everywhere at once. Instead, it continues indefinitely in some regions, spawning bubble universes where local conditions settle into different configurations. Each of these universes could, in principle, possess its own physical constants, its own laws, even its own dimensional structure. Some might expand too quickly for galaxies to form. Others might collapse almost immediately. A few, by chance, would have the delicate balance necessary for complexity, and in one of those we find ourselves. This framework introduces the anthropic principle in its most expansive form, the idea that the universe we observe is conditioned by the requirement that observers exist within it. It does not explain why the constants of nature take their observed values in any fundamental sense, but rather reframes the question, suggesting that many values exist, and we inhabit one of the rare viable combinations. Critics argue that the multiverse risks stepping beyond the bounds of empirical science, as other universes may be fundamentally unobservable. Proponents counter that it emerges naturally from well-established theories and may leave indirect signatures, subtle imprints from collisions between bubble universes or statistical patterns in cosmological data. Even within our own universe, the dominant components remain largely mysterious. Dark matter and dark energy together account for approximately 95% of the cosmos, yet their nature is still unknown. Any complete account of the universe's beginning must ultimately explain not only visible matter, but these hidden constituents as well. Dark matter, inferred from its gravitational effects, appears to have played a crucial role in the formation of structure. Without it, galaxies would not have formed as quickly or as efficiently as they did. Yet, despite decades of searching, no definitive detection of dark matter particles has been made. Dark energy, even more enigmatic, drives the accelerated expansion of the universe. Its origin is often associated with the energy of empty space itself, a concept that emerges naturally in quantum field theory, but whose observed value is vastly smaller than theoretical predictions. This discrepancy, sometimes called the vacuum catastrophe, is one of the deepest puzzles in modern physics. Some recent theories suggest that dark energy may not be constant, but evolving over time. If so, it could be intimately connected to the processes that governed the universe's birth, offering a potential bridge between early and late-time cosmology. To understand the beginning of the universe fully, one must also look toward its end. The equations that describe cosmic evolution do not distinguish between past and future. They trace a continuous arc from origin to destiny. In this sense, the fate of the universe is the mirror image of its birth. If dark energy remains constant, the universe will continue to expand indefinitely, growing colder and more diffuse. Galaxies will drift beyond each other's horizons, stars will exhaust their fuel, and the cosmos will approach a state of thermodynamic equilibrium, a heat death in which no free energy remains to sustain structure or activity. Yet alternative scenarios remain possible. If dark energy evolves or reverses, the expansion could slow, halt, or even reverse, leading to a future contraction, a potential precursor to another bounce. In more exotic models, the universe could undergo a big rip, where the fabric of space-time itself is torn apart. Each of these endings carries implications for the beginning. A cyclic universe suggests no true origin, only an infinite sequence of transformations. A heat death implies a one-way journey from order to disorder, rooted in the low entropy state of the early cosmos. In every case, the end is not separate from the beginning, but a continuation of the same underlying narrative. There is a final, unsettling symmetry in the story of the universe, that the same processes which gave rise to galaxies and stars also gave rise to minds capable of reflecting upon them. Consciousness, in this sense, is not an external observer, but a product of cosmic evolution, a way for the universe to become aware of its own existence. From the first fluctuations in a quantum field to the firing of neurons in a human brain, there is an unbroken chain of causality, a continuous unfolding governed by the same physical laws. The beginning of the universe is not merely a distant event. It is the origin of every thought, every question, every attempt to understand. And yet, despite all that has been learned, the deepest questions remain unanswered. Why does anything exist at all? Why these laws rather than others? Why a universe capable of complexity rather than one that dissolves into simplicity or chaos? These are not questions that yield easily to experiment or equation. They lie at the boundary where physics meets philosophy, where empirical inquiry gives way to reflection. And it is here, perhaps, that the story of the universe's beginning becomes something more than a scientific account. It becomes a meditation on existence itself. Let us return one final time to the beginning, not as a boundary beyond comprehension, but as a sequence, fragile yet profound, unfolding within the first second of existence. In that instant, the universe transformed from an unknowable quantum state into a structured, evolving cosmos. It is here, compressed into a span smaller than any human intuition can grasp, that the foundations of everything were laid. At a fraction of a trillionth of a second, forces that may once have been unified began to separate, each acquiring its own identity. Gravity decoupled first, followed by the strong nuclear force, and later, the electro-weak interaction split into electromagnetism and the weak force. These transitions were not merely changes in behavior, they were phase shifts in the nature of reality itself, akin to water freezing into ice, but at energies beyond imagination. As inflation drove the universe outward, quantum fluctuations, tiny random variations in energy, were stretched across vast scales. These fluctuations became the blueprint for all future structure. Without them, the universe would be perfectly uniform, devoid of galaxies, stars, and life. It is a startling thought that all complexity arises from microscopic uncertainty magnified by cosmic expansion. By the time a single second had elapsed, the universe had cooled enough for neutrinos to decouple, streaming freely through space. These ghost-like particles still permeate the cosmos today, relics of that primordial era. Though difficult to detect, they carry with them information about conditions mere moments after the beginning. What, then, is the beginning of the universe? Is it a singular event, a bounce, a transition, or an emergent phenomenon? The answer, at present, is that we do not know, and perhaps more importantly, that the question itself may admit multiple equally valid interpretations depending on the framework applied. In the standard cosmological model, the universe begins in a hot, dense state and evolves according to well-tested physical laws. In quantum gravity models, that beginning is softened, replaced by a finite, describable state that avoids infinities. In cyclic theories, the beginning is merely one phase in an eternal sequence, and, in multiverse scenarios, it is one instance among countless others. These perspectives are not necessarily mutually exclusive. It is possible, perhaps even likely, that the true description of the universe's origin will incorporate elements of several frameworks, unified by a deeper theory not yet fully realized. Just as relativity and quantum mechanics once seemed irreconcilable, only to reveal overlapping domains of validity, so too might our current models converge. Science advances not by replacing one story with another, but by refining its narratives, by expanding their scope, increasing their precision, and integrating new evidence. The beginning of the universe is not a fixed answer waiting to be uncovered, but a dynamic understanding that evolves with each generation of inquiry. There are boundaries beyond which observation cannot pass. The cosmic microwave background forms a kind of horizon, obscuring earlier epochs from direct view. Even gravitational waves, which may one day probe deeper, will encounter limits imposed by the physics of detection and the nature of space-time itself. Beyond these limits lies a domain accessible only through theory, through mathematical structures that extend beyond empirical verification. This is both the strength and the vulnerability of modern cosmology, its ability to describe realms far beyond direct observation, and the challenge of determining which descriptions correspond to reality. Yet history suggests caution in declaring any boundary absolute. Each generation of instruments has revealed phenomena once thought inaccessible. What is hidden today may become observable tomorrow as technology advances and new methods emerge. Still, there may remain questions that are fundamentally unanswerable, not because they lack meaning, but because they lie outside the domain of testable science. The origin of the laws themselves, the reason for existence rather than non-existence, these may forever reside at the intersection of physics and philosophy. To speak of the universe's beginning is to tell a story, a narrative shaped by observation, guided by theory, and enriched by imagination. It is a story that begins in simplicity and unfolds into complexity, that transforms energy into matter, matter into structure, and structure into awareness. In this narrative, the laws of physics serve as both script and constraint, dictating the possible paths along which the universe can evolve. Yet within those constraints, there is room for variation, for contingency, for the emergence of patterns that were not predetermined in detail. The galaxies that fill the cosmos, the stars that light them, the planets that orbit those stars, all are chapters in this unfolding story. And within one small corner of one galaxy, the story has become self-aware, capable of reflecting upon its own origins. This capacity for reflection does not stand apart from the universe. It is a continuation of the same processes that began in the earliest moments. The atoms in our bodies were forged in stars, the structures of our brains shaped by evolutionary pressures, all ultimately traceable to the initial conditions of the cosmos. The beginning of the universe is not a point we can visit, nor a moment we can fully reconstruct. It is an asymptote of understanding, a limit toward which our knowledge approaches, but never quite reaches. And yet, in that approach, there is meaning. We have learned that the universe is older, larger, and more intricate than any prior generation imagined. We have traced its history back billions of years, reconstructed its early conditions, and identified the processes that shaped its evolution. Each discovery has brought us closer, not to a final answer, but to a deeper appreciation of the question itself. Perhaps the most remarkable aspect of this story is not the beginning itself, but the fact that it can be known at all. That a species arising on a small planet, orbiting an ordinary star, can uncover the history of the cosmos. This is a testament to the power of reason, observation, and curiosity. In the end, the beginning of the universe is not only a scientific problem, but a human one. It speaks to our desire to understand where we come from, to situate ourselves within a larger context, to find coherence in the vastness that surrounds us. And so the story remains unfinished. New observations will refine it, new theories will reshape it, and future generations will see further than we can. The beginning of the universe is not behind us in any final sense. It is a question that continues to unfold, as boundless as the cosmos itself.